This is the video I made just for the continuous from our previous discussion last time. We did cover until round robin and all the example we have been discussed together. So now we're going to directly go and discuss on term of quantum. Okay, time quantum and contact switch time. The performance of round robin algorithm depend on the size of the time quantum. So if you have a different size of time quantum, you're going to get a different result. If the time quantum is extremely small, if let's say you have 1 millisecond, so round robin can result in large number of contact switches. So let's say you can see here, this is your your process time. Example, now you have 10. Your time for the process, you have 10. And then it mentions that the quantum will be at 12. So each 12 is going to have one quantum. Another 12, it will be another quantum. So you can see here, at 10, it's not even reached 12. So that's why you cannot see any quantum in between the process. So the contact switches is 0. The second example here, your quantum is at 6. Times 6 is going to have quantum. If let's say you have until like 12 here, you have another quantum. So now in between 0 to 10, you're going to have at 6 first quantum. So that's why you have one quantum only until 10. If you are until 12, you're going to have another one, 12, 2, and so on. Okay, let's say you can see also about the third example here. We have a quantum of 1. So each one, like maybe example here, we put as millisecond or 10 second. So every 1 millisecond is going to have a quantum. So one quantum, next until each 1 second. So all together you can see you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, 1, 2, 3, 4, 5. Okay, in between you can see until 10 here. In between until 10, you're going to have in between is 9 contacts of switching. This one is you already finished or the process time. So in between you're going to have 9. So this is how quantum affect your round robin. And for this slide is also mentions about the turnaround time, which effect when you have a different quantum time. The average turnaround time of a set of processes does not necessarily improve as the time quantum size increase. So it's mentioned it does not necessarily improve as the time quantum increase. In general, the average turnaround time can be improved if most of processes finish the next CPU burst in a single time quantum. So here you have a time quantum, and this is the average time around turnaround time. So when you have a process P1, P2, P3, P4, you have 4 processes altogether, and the time of each process 6, 3, 1, 7. So here you have a average turnaround for each process. So as let's say example here, optimization criteria for scheduling. So you have the maximum of what is the meaning by maximum CPU utilization, maximum throughput, minimum turnaround, minimum waiting time, and minimum response time. How to delete? Wait, okay. So here let's see what is happening when you have example P1. P1 you're going to have the time is until 6. So you have until 6 here, and then you have another one P4 until 7. You have P1 P3 and until 1 only, and another one is P2 until 3. But you need to calculate, you need to draw your P1, P2, P3, and then you're going to calculate how many turnaround time that will affect your process. This one last time you already know how to draw, and you know how to calculate and measure the turnaround. So this is a example of the graph. So let's see the example here, example 7. We have example 7 in terms of ABC. Let's say the time quantum in example A is 10. While time quantum for case B is 5, and another one is 1. This is example similar to this here. Okay, but okay, this one is slightly different. Just now it's 6, now it's 5, but it's okay. You can see, let's say we have the maximum of 10 here. Not 10, I guess more than 10. 1, 2, 3, 6, 7, 8, 10. But this one is calculate 10. Supposedly it is supposedly until here if it is 10, but it's okay. It is not following the exactly the graph, but you can see time content if it's 10. If 10, you can see context switches of 3 different quantum for job A, which require only 8 cycle to run the completions. Oh wait, this is not related to here. Okay, this is just example. So you have 8 cycle to run the completions, because you have the quantum is 10. We are until here, and finish before the time quantum expired at 10. Okay, so assume that job A having 8 cycle. Finish before expired, which is 10, isn't it? So for B and C, the time quantum expired first. You can see the time is expired first, interrupting the job. So you're going to finish job A first, and then you're going to continue the job B. So it's the time quantum expired first, it interrupt the job. So when let's say you have cycle job A, supposedly is going to be have 8 cycle. It's supposedly until here, but at 5 it's already meet the time quantum. That's why you're going to stop the job A first, and then you need to do another job, isn't it? Then later on, if let's say you finish the job B, going to start with job A back, and job B, job A, and job B. If you still remember the previous example for here, it's quite similar, but now you are depending on the time quantum. Okay, here job A supposedly is until 8, right? But it's going to be effect and stop because you have a time quantum at 1. So at each one time is going to stop and interrupt the job. Okay, for for case A, there is no contact switch because you finish first, isn't it? So job A run to completion since the CPU burst and shortly before time quantum expired. No difference between if you are using the RR and also FCFS policies. While for case B, there is one contact switch for the rest of the job A. Job A is preempted once when the time quantum expired. And for job C, you can see there is 10 contact switchings for second cycle of job A. The job is preempted every time the quantum expired because you have the expired of 1. So there is a disadvantages for B and C when you are having a overhead become costly and turnaround time suffers. So that is effect what time quantum can give for the process. Now let's move to the priority scheduling. For priority scheduling, we are having a priority number integer is associated with each process. The CPU allocate to the process with the highest priority when you have smallest integer equal to highest priority. It is can be used for the preemptive and non-preemptive. For the SJF or SJN algorithm is priority scheduling, where priority is the inverse of the predicted next CPU burst time. So what the problem is also equivalent to the starvation, which is low priority process may never execute. That's why the solution is later on you're going to have the aging. For the aging, as time processes increase the priority of the process. Let's see the example at here. We're going to consider 5 process and it give the CPU burst time already. And now we have the priority. Before this, we don't have any priority, right? Under a priority scheduling, we need to look into a priority. Although like you can see the CPU burst time is only like 1, supposedly it's going to be considered to have start first, but we need to look into the priority. So priority scheduling Gantt chart. First, you're going to do the first one, P2. Second, P5. Third, P1. Fourth, P3. And lastly, P4. So you need to also look into the CPU burst. First, 1 only. Second, 5 means plus 1 is a 5 cycle for CPU is going to be 6. After that, third will be 10. 10 all together. Fourth one is 2. 2 and lastly is going to be 1. So this will be your waiting time, waiting time, waiting time, waiting time, waiting time. And remember how to see the turnaround time, turnaround time, turnaround time, turnaround time, turnaround time for each of the process. So waiting time, first for P2, there is no waiting time because you already start it, isn't it? So you start at 0 and you finish at 1. And then what else? You're going to have the waiting time of 1 minus 1 equal to 0. Supposedly, you can just stick here 0. And P5, you start at 1 here. P1, you start at 6. P3, you start at 16. That's why there is no, your waiting time is 16. And P4 is 18. While for the turnaround time is slightly different. We're going to look into the turnaround. Here P4 is 19. P3 P3 is 18. P1 is 16. P5 is 6. And P2 is 1. Then you can do example last time. You're going to average. You're going to get the average waiting time and average turnaround time. So system administrator or process manager use different method of assigning priorities. Processor manager priority assignment methods, which is memory requirement, numbers and type of peripheral devices, total CPU time, and amount of time already spent in the system, which is aging. This is the one that we're going to look into later on. So there is another exercise. This one you can try to do it. You can use FCFS, SJN, and parity. Try to do all these three algorithm and method. See what is the difference in terms of the average. Which one is the best in terms of average waiting time and turnaround time, and you need to know why. Okay. Okay, I guess the video is going until here only. Later on, we're going to do a multi-level queue later on. Okay, so now combining priority scheduling and RR, system execute the highest priority process, which is process with the same priority will run using round robin. It gives you the quantum equal to. Consider 5 processes and their burst time. So you need to also look into the priority. First is P4, second is P2 and P3 is similar priority. After that, you can see because it's a similar priority, then you need to also look into the burst time. So which one is the smallest? This one. So P2 will be second, P3 will be third. After that, similar priority again. You're going to do what? You're going to do a burst time. Which one is the smallest? So the smallest will be P5 and then P1. But you're going to see it will be continue later on after the because there is a interrupt. You have the quantum too. So priority Gantt chart. How you going to do the priority Gantt chart here? Every quantum 2. So system execute the highest priority process. Process with the same priority we run with the using round robin and quantum 2. It's mentioned only a same priority. That's why this and this will be having quantum 2. This and this will be having a quantum 2. Let's see the first one. P4. The priority, high priority is going to do directly all the process, which is 7. So it's finished already. Now we have the problem, which is SAM parity. Will be run using a round robin, which is quantum 2. Okay, round robin, which is quantum 2. That's why first P2, you can see here, P2, you're going start here, but you have the 2 quantum 2 here. And after that, you're going to interrupt and continues with another one, which is similar parity. You're going to have another 2 quantum and interrupt. Okay, you're going to interrupt because you see, process with the same parity we run using round robin. You follow the round robin style, and you're going to interrupt each quantum 2. After that, after you finish with 3, still left, you can see you have another 3 for P2, isn't it? That's why you're going to continue with P2, but only 2 again because it's having a quantum 2. And continue back with P3, another 2. Minus 2, you're going to have 6. Minus 2, you're going to have 1 left here. After another 2, you're going to continue with P2, but here is 1 only because now left only 1 for the burst time for P2. That's why here is 1. So you need to calculate it carefully. For our P3, we have another 4. So after it finish, we have another 4, right? After we finish the same quantum, you can see P2 is already finished. So that's why it's directly will do for the P3 now. 4 cycle. Another 4 left. So it's not going to consider P2 anymore because the parity for P2 is already finished. So no quantum 2 anymore. And directly P3. Now you're going to continue the similar thing because here and here are having a similar parity. So please remember similar parity, same parity, going to have a quantum 2. After finish P3, you're going to start, which one will be start first? Here, P3 using a round robin. This one will be start first, 2 only. So minus 2, you're going to have another 1 after that. After 2 here, you're going to continue with P1, but only 2. Remember, minus 2, you have 2. Now you go back to the P1, P5, but it's only 1 here. And for P2, you have another 2. So it is not too hard for this combination parity scheduling and RR round robin. It's quite easy, but you need to make sure you understand the statement. After that, you can calculate the average waiting time and also turnaround time. This one here for the left side is a waiting time, and for the right side is your turnaround time. Okay, you need to calculate. Last time we done already how to calculate the waiting time and turnaround time. I guess only that. After this, we have much more complicated when we have another 4 cases to look into under multi-level cube. Okay, thank you for the watching and stay safe. Bye bye.